available in our YouTube channel. The seminar has a YouTube channel now. I think I sent to everybody. I'm going to send again this week. Also, if you have any colleagues who would like to receive the newsletters, let's call it that way. I send every Tuesday, Wednesday, and Thursday, I send the reminders of the seminars. So anyone who wants to include a colleague, please send me an email. I'm going to place my email here. So that I can include the names in the email list. So it's a pleasure to have Ana Luiza Ferrari talking to us today. Ana Luiza is a very young researcher. She did her undergrad in São Carlos, USP-São Carlos, and now she's doing, I didn't know that was a possibility, she's doing a dual master's. She's doing her master's at the same time doing a master's in São Carlos and a master's in Cologne. In reality, she's talking to us from Cologne right now. So, being a very young researcher, I don't have too many things to say about her. Just that she participated in the school we had here 2 years ago that was taught by Professor Zitko on NRG. And she is going to talk to us about NRG today, but a new formulation of NRG. Real space formulation of the numerical renormalization group method. She did in collaboration with Professor Luis Nunes de Oliveira from São Carlos. So thank you very much. You may start.
Thank you. So good afternoon. My name is Ana Luiza. I'm a Master of Science student at the University of São Paulo and at the University of Kondo. This research was developed at the University of São Paulo with Professor Luis Nunes de Oliveira and was funded by CAPES. It is called a real space formulation of the numerical renormalization group method. So let us begin by a brief history of the problem and by the specific goals of this research. So we start in 1934 when experimentalists in the Netherlands found an anomalous resistivity minimum for impure gold. At that time, the minimum could not be explained because there were two mechanisms to explain resistivity. One were the lattice vibrations, and the second, the number of impurities. As the temperature decreases, the lattice vibrations decrease, and the number of impurities remains the same. So, at that time, nothing could explain why the resistivity went back up. It was only in 1964 that Kondo made his contribution, which was so important that the anomaly is now called the Kondo effect. So, Kondo attributed the anomaly to magnetic impurities in the material, and he created a model Hamiltonian in which an impurity spin couples to a conduction band of electrons via an exchange interaction J. He then applied perturbation theory up to the third order of this parameter J, and he found a contribution to the resistivity proportional to the logarithm of temperature. Now, as the temperature decreases, the logarithm increases, so the minimum was successfully explained. But a new problem arises, because at zero temperatures, the solution diverges. So in the next decade, physicists tried to add more perturbative terms to see if this could get rid of the divergence. And it didn't. The Kondo problem was only solved by Wilson in 1975 when he developed the numerical renormalization group, which is a non-perturbative method. At zero temperatures, NRG tells us that the solution to the Kondo problem is a singlet state. The ground state is a singlet state between the impurity and the conduction band. Moreover, it also tells us that we can describe the system by a fixed point Hamiltonian in which the parameter J is effectively infinity. So if J is going to infinity, it is not a small parameter to be treated by perturbation theory. So this is the reason why Kondo's approach failed for temperatures smaller than the Kondo temperature. And then in 1994, NRG was first applied to calculate transport properties, which is something that we'll do here. And in the last decades, the interest in this physics and in this method only grew as experiments with nanodevices advanced, because nanodevices are the best experimental platform for this research. So here we'll study a quantum dot side-coupled to a quantum wire. In the next slide, I'll mention how to generalize our method to other geometries of the single impurity Anderson model. This model is shown here. So the first term is the tight binding approximation, the conduction band is the tight binding approximation, where one electron is able to hop onto its neighboring sites. Then we have a gate potential Vg applied to the quantum dot. This controls the occupation number in the quantum dot and can be controlled experimentally. A double occupation in the quantum dot is penalized by an energy U. So this term is the Coulomb repulsion. And at last, one electron from the dot can hop onto the central site and vice versa due to this hybridization term. Our first goal is studying universality, a term I'll define later, in three properties. The conductance was already studied in a 2009 paper by Yoshida and al. Here, we extend these concepts to two other properties, to the thermoconductance and to the thermopower. This is advantageous because it provides theoretical predictions for these quantities, and because it allows a linear mapping between experimental data and non-universal functions, like I'm showing here. Our second goal is developing the exponential NRG, which is an alternative to Wilson's NRG with a simple formulation that accommodates wire potentials more easily and that works with a realistic dispersion. By this I mean that in this method we are indeed working with the cosine dispersion that comes from this tight binding chain. We don't assume a linear dispersion of the conduction band like it's usually done with NRG. This is interesting because it allows a more faithful comparison between the ENRG and other methods, because these other methods also don't assume this linear dispersion. And we have a pedagogical advantage because the ENRG is easier to learn. The ENRG can be applied for any geometry of the single impurity Anderson model. This can be easily seen when we remember that any geometry can be mapped onto this three-diagonal chain by a Length transformation. So here we are working with this side-coupled device, and we took all these hopping coefficients to be the same. So we have a special symmetry about this axis, an inversion symmetry. In this case, the Length transformation takes a simpler form, which is the even-odd transformation that I'm showing here. After the transformation, the resulting Hamiltonian will be the sum of an interacting and a non-interacting part. We only take the interacting part into consideration, which is just this three-diagonal chain. And this problem can present another type of symmetry that comes when the Hamiltonian is invariant by a particle-hole transformation. This transformation doesn't change the conduction band part of the Hamiltonian, and it doesn't change the hybridization term too. So we only have to worry about the quantum dot. And as the name suggests, the transformation swaps annihilation operators, so holes, and creation operators, particles. By doing so, it takes the gate potential Vg into minus Vg plus U. So it changes the Anderson impurity model. And then we can expect that the uncoupled quantum dot subspace, it also changes from before to after the transformation. But for a special choice of parameters, if we choose Vg to be minus U over 2, then the Anderson impurity model doesn't change and we have particle-hole symmetry. In this case, the uncoupled quantum dot subspace doesn't change too, and we see that there is a clear symmetry because we have to pay the same energy price to remove one electron or to add one electron. So this manifests with this particle-hole symmetry. Another important concept for what will come is the concept of the Congo regime, because universality is only valid in the Congo regime. To explain what this regime is, this image is useful. So here, the lowest line levels represent the ground states of each of these quantum dot configurations below in pink. The columns are the possible excitations. If we have a non-zero hybridization V, then all these levels will acquire a certain width characterized by this parameter gamma. And the states of the different columns, they can mix. In the Kondo regime, we'll say that the energy, the thermal excitation energy, and the width acquired by the levels gamma, they must be much smaller than this energy and then this energy. So, and then the bandwidth too. So we see that in the Congo regime, we don't have enough energy to promote charge fluctuations in the quantum dot. And the occupation number in the quantum dot is always approximately 1. And also, in the Kondo regime, we cannot be too far from the symmetric point, because this inequality doesn't hold for both these columns in highly asymmetric cases. So, in the Kondo regime, the occupation number is approximately 1, we are not too far from the symmetric point, and universality is valid, and also the Schrieffer-Wolff transformation. The numerical-renormalization-group, then, is an efficient method for solving quantum impurity systems. Even though it is historically associated with the Kondo problem, its applications are more general. It can be applied whenever we have a quantum impurity coupled to a non-interacting path of fermions or even bosons. The first step in Wilson's NRG is the discretization of the conduction in momentum space. Any numerical treatment of this infinite chain, this infinite Hamiltonian, would require some form of discretization because we cannot implement infinite dimensional matrices. However, not all discretization schemes are good, and there is an apparent reason why we must use the logarithmic discretization. So for instance, in the Kondo problem, the Kondo temperature sets a very small scale, and the relevant physics happens in a small window around this temperature. If we want to describe Kondo physics with a linear discretization, we would need minimal energy intervals, at least of the order of the Kondo temperature. To get those minimal intervals, we would have to work with unrealistically large matrices. So this makes describing Kondo physics with a linear discretization an impossible numerical problem. A logarithmic discretization avoids this problem by having a high resolution only at low energies, where the Kondo physics takes place. And this discretization has yet another important characteristic because it preserves this scaling invariance of the conduction band. The original undiscretized conduction band has scaling invariance. It doesn't have a characteristic energy scale apart from the bandwidth. And we can see that this logarithmic discretization doesn't introduce an unphysical energy scale to the problem when we study its scaling invariance. So in this image, I have a linear discretization and a logarithmic discretization. I am multiplying both by the same factor and restricting the results to the bandwidth. In a linear discretization, we do not have scaling invariance. I can say whether I am before or after the multiplication by this factor. And I know this because the characteristic energy scale given by the separation of the levels, it grows. In the logarithmic discretization, we have scaling invariance, and we are not introducing an unphysical characteristic energy because we see that there is nothing to grow or to shrink, no characteristic energy to tell me if I am before or after the multiplication by this factor. So this is preserving the scaling invariance of the original conduction band. Now that we understand why the logarithmic discretization is important, we can go through the steps of Wilson's NRG. So the first step would be writing the Hamiltonians of the conduction band and of the hybridization term in this integral form, where these integrals go through the whole conduction band. Then we do the logarithmic discretization. So we divide the energy intervals like this, where the size of the intervals is defined by this parameter lambda. When lambda goes to 1, the size of these intervals goes to 0. So in this case, we have the thermodynamic limit, where no discretization is made. Then in Wilson's NRG, this parameter lambda is a real number bigger than 1. Then we define one fermionic operator for each interval via this equation, and we can change the basis of these integral Hamiltonians to this new basis of fermionic operators. And the resulting Hamiltonian will be an impurity coupled to all these new operators that I just defined. But I would like the impurity to be coupled to only one operator. And I can get that if I do a Langevin transformation. So by doing a Langevin transformation, I get this three-diagonal chain. But this chain has one important characteristic. Its hopping coefficients are decaying exponentially. So what this procedure is achieving in the end is that we have organized the energy scales of the problem. Because if I move further away from the impurity along this direction, I am taking into account the smaller hopping coefficients. So I'm taking into account the smaller energy scales. If we remember that what defines the relevant energy scale for the problem is the temperature due to the Boltzmann factor, where I choose to truncate this chain is related to the temperature that I want to describe. So in the end, we have a possible truncation scheme, and we have enough resolution to describe Kondo physics. I'll go back to this point after the next slide, where I go through the steps of the exponential NRG. And so the alternative method that we present here is simple. All the critical steps of Wilson's formulation are present, but now we obtain the desired results by working in real space. This image shows how we divide the conduction band sites. So sites containing operators, so we group the sites in intervals that contain operators with these indexes. So, for example, lambda is the parameter that defines the size of these intervals. If lambda equals 2, then the first interval, I1, will be equals 1. So the operator with the label 1 will belong to the first interval. I2, the second interval, will be equals to 2 and 3. So the operators with indexes 2 and 3 belong to the second interval, and so on. We see that the size of these intervals is growing exponentially. So we call this an exponential discretization. And then we define one fermionic operator for each interval. And this is the equation for the new operators. Now, there is an apparent reason behind the choice of coefficients that we see here. First, this exponential grouping of sites already ensures exponentially decaying hopping coefficients later. This is because this lambda prefactor squared, it decays exponentially as j grows. And this simply comes from the normalization of this linear combination of A operators. Then each operator belonging to the same interval must contribute to F with the same weight. But there's no restriction on this complex number here. And we choose this specific complex number so that after we change the basis, we get a chain Hamiltonian with no diagonal terms. This is not necessary, but it is done in analogy to Wilson's chain Hamiltonian, which also usually doesn't have diagonal terms. And we can discuss what is the thermodynamic limit for our discretization. So if we take lambda going to 1, we'll see that Gn is equals n. In this case, each interval will contain only one operator with the label n. If each interval only has one operator, I am mapping the chain onto itself. So lambda going to 1 is the thermodynamic limit, where no discretization was made. And in both cases, in Wilson's case and in our case, this parameter lambda, it sets the accuracy and the velocity of the calculations. So the closer we are to the thermodynamic limit, the more accurate are the calculations, but the harder it is for the computer. And we notice that in Wilson's case, his parameter was a real number bigger than 1, while in our case, we have a natural number bigger than 1. This is actually a disadvantage of our method because it limits our control over this accuracy-velocity balance. But we also have advantages, and one of them is that the method is very straightforward. So to get the chain Hamiltonian, all we have to do is a very simple change of basis in the Hamiltonian. We have to go from this basis A to this basis F. But here I notice that this transformation is not complete because we don't have the same number of operators A as we have of operators F. But again, in analogy to Wilson's calculation, where he defined one operator for each energy interval and then inverted the relation, we assume that this can also be inverted so that we can find A in terms of F. Then we only have to substitute A in the Hamiltonian to get the chain Hamiltonian in the F basis. With this chain Hamiltonian in hands, it's time to discuss the iterative diagonalization procedure. So we regard this chain Hamiltonian as a sequence of Hamiltonians truncated at different sites n. And a general term of the sequence is shown here. As expected, the hopping coefficients are decaying exponentially, and they have a much simpler form than what we have in Wilson's case. This prefactor is chosen so that the smallest energy scale in Hn is approximately unity. Then we can write a term Hn of the sequence as a function of a previous term plus a non-diagonal correction, so that I can construct the Hamiltonian in the iteration n by diagonalizing the Hamiltonian in the iteration n minus 1. So this is what we mean by iterative diagonalization. And in each step, I will have a many-body spectrum. And because I can relate where I am, in which iteration I am to the temperature, then I have one many-body spectrum to approximate the spectrum for a temperature window. If I have energies per temperature, then I can compute thermodynamic properties. So this is the idea. And in here, I am showing the conduction band energies for the NRG with lambda equals 4, and for the ENRG with lambda equals 2. And we see that this scheme is indeed achieving what we wanted because we have a logarithmic discretization in momentum space in the end. Now that we discussed the Hamiltonian Hn, it would be time to discuss the NRG and the ENRG codes. After we constructed Hn, the codes are essentially the same, and I won't go into detail of the code here, but I can recommend a paper to anyone interested. There is one thing that I would like to say, and it is that my code was written in Python with one subroutine in Fortran. This is something that I think it is interesting to mention because both the theoretical and numerical aspects of NRG can be hard to grasp for young researchers, so a combination of the exponential NRG with a Python code could be more appealing, and it is certainly possible. And what this code returns is the energy spectrum for each iteration or for each temperature window, and the matrix elements of the chain operators. Both these things can be used to compute later the conductance, the thermoconductance, and the thermopower. And another thing that is usually mentioned in the context of NRG is these flow diagrams. So here we have the many-body spectrum versus the iteration number. Although we cannot discuss much of the physics from this plot alone, there is one thing that we can say. Here we have two fixed points of the renormalization group transformation. We have a high temperature fixed point in this region called the local moment, and a low temperature fixed point called the frozen level. And they are linked by a crossover region. And the low temperature fixed point is happening for bigger iterations because this is where we take into account the smaller scales, smaller hopping coefficients, because the chain is bigger. And now we can discuss a relationship between the NRG and the ENRG. So we can find a relationship between the parameters by comparing the asymptotic form of the hopping coefficients. This is Wilson's hopping coefficient, and this is our hopping coefficient. And here in the asymptotic form, this exponential decaying behavior is more clear. And we see by comparing these boxes that the methods are equivalent when Wilson's lambda is our lambda squared. Now, in Wilson's original paper, he argued that when lambda is smaller than 3, errors introduced by this discretization are irrelevant. But for lambda bigger than 4, we should expect to see unphysical oscillations in plots of thermodynamic quantities versus temperature. In our case, the smallest possible lambda is 2, which already corresponds to lambda equals 4 in Wilson's case. This means that the ENRG always shows these unphysical oscillations. In the original NRG, this is dealt with by z-averaging. So here we have to discuss how to deal with these oscillations. And this is what I am showing in the second part. So what we do is we add to the results of the discretization that I showed the results of a second discretization that starts one cycle later. And when we do this, we see that the results of these discretizations, they both oscillate, but the oscillations exactly cancel out. So by averaging them, I get, in this case, the conductance that I want with no unphysical oscillations. And in fact, we don't have to start the discretization on the first or on the second site. We can start it many sites later. In practice, what this accomplishes is a better description of the high temperature physics, but we didn't do that here. And now we can move on to the second part of the talk, which is universality. So as I showed on the flow diagram of the last slide, we have in the Kondo regime two fixed points, the frozen level and the local moment, and they are linked by a crossover region. Again, this image is useful to explain what these fixed points are. So the difference between them is the temperature, or in other words, how many excited states I can access. In the local moment, because we have higher temperatures, I have higher thermal excitations. And in fact, this thermal excitation energy is much higher than this energy gamma that defines the coupling between the conduction band and the impurity. So that in the local moment, we can describe the system by a system where we have a spin effectively decoupled from the conduction band, so that the fixed point Hamiltonian is a simple conduction band Hamiltonian. In the frozen level, we are at low temperatures. In fact, we are dealing with temperatures smaller than the Kondo temperature defined by this energy window. In this case, we have the formation of the Kondo singlet, where the electron of the impurity is completely screened by the electrons of the conduction band. In our geometry, for example, this means that the central site will be very strongly coupled to the quantum dot to form this Kondo singlet. And they are so strongly coupled that they effectively decouple from everything else, which means that again, I can describe this fixed point by a simple conduction band Hamiltonian, but with two less sites. And we chose to represent the operators which diagonalize the local moment Hamiltonian by G. Then in the Kondo regime, we also know that the Schrieffer-Wolff transformation takes the Anderson model into the Kondo model. So in this Kondo regime, I can rewrite the Anderson Hamiltonian like this. In the symmetric point, because Hj has to be particle hole symmetric, this potential W must be zero. Moreover, if we are at high temperatures, we saw that this is irrelevant, because this is what couples the impurity and the conduction band. So in the symmetric point, we can compare Hj with HLM, and we'll find that A is equals G. We then perform a change of bases in this Hamiltonian to the spaces of operators G. In the symmetric point, this transformation does nothing because Hj was already in the basis G. So we see that delta is pi over 2 in the symmetric point, so that I can recover J. But this is valid in any point of the Kondo regime. And this Hamiltonian has the form which motivates us to study universality, because it is a fixed point Hamiltonian plus an operator that drives the system from one fixed point to another. Now, let us think that we are gathering physical information about two different points in the Kondo regime, A and B, as we move along the temperature. Okay, so the starting points for these trajectories is the same, it's the frozen level. And the end point is also the same, it's the local moment, because they are fixed points. We would like to know how this operator makes the trajectories of A and B in temperature space different. And it turns out that if I rescale everything by the Kondo temperature, A and B are indistinguishable. And this is what we mean by universality. Of course, this has to be verified. So this is what I am showing on this GIF. So here I am plotting the many-body energy spectrum for two different NRG runs. I am maintaining the scale of the green curve fixed while stretching out the scale of the purple curve. This is equivalent to renormalizing the temperature, because we saw that this iteration number n is related to the temperature. And we see that there exists a number c for which these two many-body energy spectrums become indistinguishable. So this is what verifies universality. And then if universality is verified, any physical information that I may want from the Hamiltonian Hj, so its many-body energy spectrum, the matrix elements of G, the matrix elements of phi, can be calculated in any point of the Kondo regime, and I will find the same result if I rescale things by the Kondo temperature. So, for example, we call these matrix elements universal matrix elements, and we can compute them in the symmetric point for simplicity. Our goal is to calculate the conductance, the thermopower, and the thermoconductance. They can all be written in terms of these energetic moments, shown here. In the side-coupled device, they depend on this matrix element of the central side, and on the single electron transistor, it would depend on the quantum dot operator D. But this matrix element is not universal, because it is not something I get from the universal Hamiltonian Hj from the last slide. So the idea in this universality study is to rewrite this matrix element in terms of the universal ones, so phi 0 and phi 1. And we find that these constants depend on the parameters, but only on the phase shift. So these are the constants that we found. Specifically in the symmetric point, where delta is pi over 2, we find that alpha 1 is 0 and alpha 0 is 1. So the matrix element for A0 is the matrix element for phi 0. So we can rewrite these energetic moments with these matrix elements, and this is what we. So now these three functions that carry the temperature dependence, they are universal. They can be computed in any point of the Kondo regime. But it would be nicer if the energetic moments depended on only one universal function and not three. And we can get there if we make two considerations. So first, we can rewrite the spectral function ρ0 and ρ1 in terms of each other. So we can rewrite actually ρ1 in terms of ρ0, so that we can rewrite this energetic moment in terms of this one. And we can also make symmetry considerations, because this spectral function is an odd function, so ρ01 is an odd function, and ρ11 and 00, which only depend on phi 00 and phi 11, are even functions. So sometimes this integral vanishes. With these two considerations, I get the energetic moments in the simpler form, where they only depend on one function each. And as I said, these functions are universal. So the temperature dependence is restricted to universal functions, and the particle Rho asymmetry restricted to these delta coefficients. But how do we actually compute these universal functions? Well, the NRG will return the energetic moments, L0, L1, and L2. If we do one NRG run in the symmetric point, we'll have that this cosine squared is 0, and this is -1. So the energetic moment is the universal energetic moment in the symmetric point. This is true for L0 and L2, but it is not true for L1. This is more complicated, because in this case, this sign of 2 delta vanishes, and the energetic moment in the symmetric point is identically 0. But this is not really a problem. Then all we have to do is an E-energy run in a point a little away from the symmetric point, and then by knowing the phase shift, we can just divide this function by this prefactor and get the universal function. So now I can show the results that we get. All the results are color-coded. These are the colors. And here we have the gate potential, the phase shift, and the Kondo temperature. And we used in all energy runs U equals 10T and V equals 0.9T. So this teal color is the symmetric point. Here I am showing the conductance, the thermopower, and the thermoconductance computed by E-energy runs. We see that the conductance and the thermoconductance, they have a very similar behavior. They both go from 0 to a maximum value, increasing monotonically. In the conductance, this maximum value is 1, and in the thermoconductance, it is pi squared over 3. If we divide this maximum value by this one, so the thermoconductance times beta by the conductance, we will get pi squared over 3, which is the constant from the Widman-Franz law. But the thermal power has a very different behavior. It changes a lot as we vary the gate potential. It is identically zero in the symmetric point, as we could have predicted because the energetic moment L1 is identically zero in the symmetric point. And here we chose values for the NRG runs with gate potentials smaller than the one in the symmetric point. And by doing so, we got curves for thermal power which are negative. If we had chosen values bigger than the symmetric point, we would get positive curves. So we see that this quantity is so sensitive to particle Hall asymmetry that it even goes from a negative to a positive value. And we also computed this figure of merit, ZT. So we say that if we had found a figure of merit bigger than 3, then we could use the thermoelectric properties of the material to make practical applications. So to create refrigerators or power generators based on these thermoelectric properties. In our case, we found 0.25, which is very far from 3. So we say that our device doesn't have practical applications in this sense. And practical applications would be hard anyway, because all the interesting physics seems to be happening around the Kondo temperature, and this temperature is of the order of 1 Kelvin. So it is very cold anyway. And then with the ENRG runs, we can also compute the universal curves, which is what I am showing here. The curve N0 is related to the conductance. It is actually the conductance, and it is this curve. And the curve L01 is the dotted curve related to the thermal power. And N2, the dashed line, is related to the thermal conductance, and it is on this scale. It is the only one on this scale. And now that we have the universal curves, we can study the universal mapping because of these equations. So here I am showing the energetic moments, the 3 energetic moments, and we are comparing the results of ENRG runs, which are the field markers, with the results from the universal mapping, which are the lines. So as we see, we have a very good adjustment between the two approaches, which is good news, except for this region. And on this slide, I would like you to notice that this is happening for temperatures bigger than the Kondo temperature on the yellow curves, where the Kondo temperature was already big. Another way to represent this universal mapping is by plotting the energetic moments versus the universal functions. And due to this universal mapping, we expect to see lines, which is indeed what we see. All with good adjustment, except those points that I pointed out on the last slide. But if we remember that universality is only valid in the Kondo regime, and the inequality from the Kondo regime tells us that the thermal excitations must be much smaller than the bandwidth, then we understand why these points are not falling over this line. They aren't supposed to, because in this region, universality is no longer valid because we are leaving the Kondo regime. We are at temperatures bigger than the Kondo temperature, and the Kondo temperature is already big. So all is well. So now just to give an overview of what was said, here we created a new method, an alternative to Wilson's method, which is more general and easier to learn. It is called ENRG, exponential NRG. So far, it can be applied for any geometry of the simple impurity under some model. And we do the discretization in real space and not on momentum space by just grouping the sides in exponentially increasing intervals. So we got results from the ENRG runs. And we also got results from the universality study. So we studied a universal mapping for these 3 energetic moments, L0, L1, and L2. And they can be used to compute the conductance, the thermal conductance, and the thermal power. We found this relation in terms of universal functions, which can be calculated in any point of the Kondo regime, if I rescale things by the Kondo temperature. And all temperature dependence is now restricted to these universal functions, and all particle Hall asymmetry restricted to this coefficients delta. We computed the universal functions with NRG runs. These were the results. And then we can compare the results from both approaches. This is what we did in this part, where the NRG runs are the field markers and the universality predictions, the lines. And everything worked out well. We found a good agreement between the two approaches, except on one region, but we do understand what was going on there as well. So thank you.
Thank you, Ana Luiza. Very nice talk. Very good. One of the best intros to NRG that I have watched. Thank you very much. Questions? Any questions?
Can I start?
I have some questions.
Okay.
Eduardo, go ahead, please.
Okay, thank you. Edson, I guess you can ask after me. I'm sorry. I was having problems with my camera here. So first of all, let me just repeat what George said. It was a beautiful talk, very well explained, and the results were very interesting and very refreshing in this subject. Congratulations on your work. I actually have probably more than one question, but let me focus on two that are, I think, more important to me. First of all, regarding the results, you have results on conductivity, thermal power, and thermoconductivity. Did you make any attempt to compare with experimental results in typical Kondo systems? Well, let me tell you why I say that, because in my experience, the thermal power, which, as you showed, is very sensitive to particle hole asymmetry, is all over the place. I mean, you can see experimental results which are positive or negative, just like you showed, and this is consistent with what you showed, that it's very sensitive to particle hole asymmetry. And I don't know much about thermoconductivity. Thermoconductivity has the problem that you have to separate phonons from electronic contributions, so it's not easy. But anyway, can you say anything about trying to compare your results to experiments on these three quantities?
Yes, I know that in February of this year, there was a paper out. I think one of the authors is here now. Where they try to compare these results from universality studies on the single electron transistor with experimental results. And they had trouble finding this data versus temperature. And this was for the single electron transistor, which, from what I understand, is somehow easier to get experimental results from. So in this case, in the side coupled device, I don't think we would find any experimental results yet to make this comparison.
Okay, so what you said that they had problems finding. What do you mean? They did not match the theory, or they could not measure it?
It wasn't a theoretical paper. They could not find experimental results for what they were trying to compare. They weren't available yet.
Okay, yeah, but even in Kondo systems, like impurity systems, there's years of experiments on these systems. It might be worth a while to have a look at those systems.
Yes, sure.
I know that at least thermal power, I think there is a lot, but as I said, it's all over the place. But anyway, It might be interesting to try to see what happens there. The other thing that I wanted to ask is regarding the method itself. There is this difficulty with impurity problems where you have structure in the dispersion of the conduction electrons. So two cases come to mind: when there's a gap, like in a superconductor, or when you have disordered systems where you have structure on the scale of the disorder, which can be very fine oscillations in the density of states. Do you think this method can address those problems?
I wouldn't know how to answer that. Maybe Professor Luis can give you an answer.
Okay.
The answer is, I don't know. It is more general than well method, right? So in principle, we could look for that, but I can't give you any. Certainly in the case of impurities, it's the than Wells because we can't change what's happening in the real space as you wish. You can just the potential here and there as you prefer. Right? We have tried that, but that's an interesting idea. I thought about that. Concerning conductors, I cannot really say.
Okay. Okay. Thank you very much. Once again, congratulations. Very nice work.
Edson, you have a question, Edson?
Yeah. I want to thank you for the nice talk. It's very clear. It's a pleasure to see how young people can do a very nice physics. But I have a kind of technical question, and you may have explained it already in your talk, but I probably missed it. At the beginning, you said when you map your conduction band, say, or your bulk material in this tri-diagonal matrix where you have no diagonal term in the couplings. In general, when your in traditional NRG, when your conduction band has no particle hole symmetry, you have diagonal terms. So this is a complication here. For instance, if your system does not have particle hole symmetry, not on the local impurity, but for some reason you have some chemical potential in your system. So can you include the? I think you can, right? Include the diagonal term in the tri-diagonal Wilson-like chain, right?
So if we have potentials on the wire, if this can be included to the problem.
So if you have, essentially, if you have no particle hole symmetry in the bulk material. So
okay,
these appear. Okay, sorry. Go ahead.
If we don't have particle hole symmetry in my single impurity Anderson model, this is dealt with by this procedure normally. We just do this change of basis. It is not an issue. And we don't have diagonal terms, even if we choose values of the gate potential which are not in the symmetric point because of this choice of complex numbers. You can see this in the calculation.
So in this, so in this scheme, you never have the diagonal term, right? So this, okay. All right.
That, I think you misunderstood the question. Edson was asking about non-diagonal terms or particle hole asymmetry in conduction band, not in the impurity.
Oh, okay.
Okay.
So
yeah, that's right.
Okay.
So you see, Edson, we started out with the tight binding Hamiltonian, which is the whole symmetric. That easily show it's whole symmetric. And so that's why we got this whole symmetric discretized Hamiltonian. But start out with in which there is symmetry in the tight binding Hamiltonian, then we will end up with another discretized form, which will have to symmetry conduct that.
Okay. So my second question is, would you be able to include some different couplings, like single particle coupling, like spin orbit coupling in the conduction band? Would it still be addressable, let's say? I'm asking that because this is very important issue these days.
I don't know, how would that appear in the Hamiltonian?
Okay, so I'm probably you could still, even with spin orbit, if you diagonalize your Hamiltonian with spin orbit, you could map your, maybe you still can do it, because you can map your Hamiltonian in a certain form that you can later on map into your Wilson-like chain.
I think if you can map your Hamiltonian into this form, I don't think it matters if the hopping coefficients are different. I think it's okay. I don't think they can increase very much. Maybe there is some restriction like this, but I think it is possible to do this procedure. Even though we took the hopping coefficients to be the same, if they were different, it would be okay. It would still have this factor. This is the important thing.
Good. I still have another question, but I think I'll leave it for.
Okay. I see that Andrew posted a question here. You can read it if you want. Maybe Andrew doesn't have a microphone, or.
Okay.
So if you could read it aloud, please.
Okay. In standard NRG, the input for the calculation is basically the Wilson chain parameters obtained by logarithmic discretization of the bed. Is your ENRG method just a new way of obtaining those chain parameters? Or is there some difference in the NRG algorithm itself? Is there a difference in the parameters between the two approaches, or is it more a different way of thinking about the discretization procedure? So the code itself is exactly the same after we construct the Hamiltonian HN. It is really not different. But I think there is a difference between the parameters. Right, Professor Luis, there is a difference between our parameters and the parameters for the NRG.
Yeah, well, the way it was done, this work, it's essentially the same. But I was trying to explain when I answered Eduardo's question, you can have a more general form for the NRG than what you have the NRG. And so in that sense, you have additional parameters synthesized into discretized Hamiltonian. So it's more general in that sense. In this specific problem we have handled, your way of describing it, Andrew, is a different way of presenting the discretization.
His mic is not working, so I will ask him if he's satisfied with the answer, or okay.
He's typing. Andrew's typing.
Yeah, he's typing. Okay. Okay, he seems to be satisfied. I have a couple of questions. I noticed that you didn't mention, you didn't say anything about the free orbital fixed point. Did you just decide? It's not a terribly important fixed point, anyways, but you decided to leave it aside, or does the method doesn't capture the free orbital fixed point?
I'm not sure. I think it does. It is for high temperatures, so I think it does capture.
It does capture. You just decided not to dwell on it. The other question is the procedure of blocking these sites looks a lot like decimation. Does it have, or did it have was that the origin of the idea to do a decimation procedure to get the new method? Maybe this is a question more to Luis, because he's
yeah.
Sorry.
No, we were just looking for doing it in real space.
Okay.
But in retrospect, realized that it's very much decimation, and it's kind of weird. Back 3 or 40 years ago, no one thought of it this way. Even before some did it use logarithmic discretization. So your point is very taken. Just to be honest, I have to say that historically it was not into this.
Okay. So if I understand correctly, a little bit on the line of what Eduardo asked. He asked about disorder. Let's say that we introduce disorder by making random modification to the hopping parameters of the chain, of the original chain. How is that going to be translated into the new hoppings between the new states? Is that because that's why I thought about decimation, because you are blocking things and then connecting the things that you blocked, and the larger is the block, the less connected it is to the other blocks, or something like that. But would the randomness of the hoppings be translated on that? I am a bit confused.
Okay, Anna, want to answer that?
You can go ahead.
Okay, you remember Anna just briefly mentioned that you can start the discretization at the first side, the second side, and you could go on third, right? You can randomize treatment of the impurities that way.
Okay.
Okay. Yeah, and it is a little bit more expensive numerically if you start out, say, at instead of starting at the first one. But the cost is minor, so you can do it very well up to perhaps 10.
Okay.
Right. So that's how I think we should handle the problem.
Okay, perfect. Any other questions? Edson said that he had another question, but do you want to ask, or we can invite Ana Luiza again next year?
Yeah, definitely. But I will take advantage that since you are in this talk, so you may help to answer this question. You know, Ana Luiza, about this method that Adrian Feguin and with George and Carlos Busser developed. The idea was to map like any lattice into a tri-diagonal Hamiltonian and using DMRD to solve that problem. So in this sense, I found it kind of similar, because you are working in real space.
Yeah.
In those cases. So how would you compare these two approaches? all of you can answer this
question. Are you asking to me or to Luis?
Anyone who can.
I don't know. Luis probably doesn't know the method because we are still developing it. But it's different in the sense that there is no logarithmic discretization in our method. So you have a little bit of difficulty to get TK. We can estimate TK, but we cannot get any precise values because there is no logarithmic discretization. We would have to go to very, very, very large chains to be able to accommodate the Kondo cloud and have all the physics well taken care of. But we can treat, in real space, we can treat any system. Well, 1D is not a big deal in this sense, but 2D, 3D, any kind of lattice, now we are doing a bit of, and as the impurity is placed in the real system, you have, like for example, in the case of topological insulators, you can place the impurity at the surface or in the bulk, and notice the big difference that there is. So that is, but there is no logarithmic discretization. Maybe that would be a way of doing it in our method. That could be a possibility. This gives me something to discuss with Adrian the next time we talk. So it will be nice to have your talk in the YouTube channel, so I believe Adrian is on vacation, so he's not here. He's in Puerto Rico right now, so he's probably in the beach. But I will ask him to take a look at your talk, and we will discuss, certainly.
But this sounds very similar because here the logarithmic discretization comes quite naturally. I think this is very charming from this method.
Yeah, and it's much easier to explain to students. I am pretty sure, because the NRG, the beginning of the NRG, the initial parts of NRG are a little bit complicated for students who are seeing it for the first time, or better, for anyone who is seeing it for the first time.
Yeah. Okay. So, thank you.
I think I see that Krisha said. Okay, Krisha worked with Adrian, so she probably knows the details of the method better than me. Yeah, that's true. That's true. They add a little bit of decay by hand. That's what has to be done if you want to include larger Kondo clouds, and you want to go to lower decays. Yeah, that's true. Yeah. But it would be nice to have another way of doing that, and that gives some ideas. Well, if there are no other questions, Edson, any more comments or questions? If not, let's thank the speaker again. Very nice talk, and I will be writing you an email asking for your talk so we can put it in our website, and I will send Lara. Lara is clapping too. Lara is clapping too. Yes, and we will be sending out an email reminding people to take a look at the YouTube site. I believe most, if not all, the talks this semester are there. I believe, I'm not sure. Edson, are all the talks already in the YouTube channel?
Yeah.
Yeah. Edson is spending a lot of time working with that. We should thank him. It's very nice to have the talks, but for people who cannot come or for people who want to watch again and take notice of the details, it's very important to have them. So thank you very much, Edson, for taking care of that.
We need to ask for a subscriber. You can subscribe to our channel. So have some extra.
We need the YouTube channel to become more popular. So so it's an incentive for us to keep doing that. So Ana Luiza, thank you so much. Your talk was great. You should be proud. Thank you so much.
Thank you.
So yeah, everybody is congratulating, and do we have how many people we had at the maximum? Edson, 30 something, right?
Say that again, please.
How many people we had at the maximum?
We had about 34.
34 people.
I have a list here.
That's a very good number. Yeah.
34.
Very good. So I hope again, if any one of you yourself doesn't receive every week my emails, or you have a colleague who would like to participate, please just send me an email and I will add the email addresses to the list so that other people can know about the talks and we can reach more people. So thank you Ana, and thank you Luis too for being here. So and thank you to everybody. We will be back next week.